Hello dear student. Today I invite you to a new lecture series in tensor analysis. This is a 16-hour module from your paper Mathematical Physics. In this lecture series, I will be mainly dealing with mathematical concept. That is, this lecture series is going to be purely mathematical as we are learning a new mathematical tool. I will be providing you with physical examples as far as possible. Tensors are a very important mathematical tool which helps us analyze many problems in physics, which includes the areas in mechanics, electrodynamics, general relativity, and others. Continuum mechanics is completely based on tensors and how we analyze and manipulate it. So today let us learn a very new tool which is going to be very helpful in your coming chapters also. So welcome to the world of tensor analysis. In this module, you have to learn about notations and conventions which is used in tensor analysis. In summation convention, you will learn about covariant, contravariant and mixed tensors, many algebraic operations which is done upon the tensors, and maybe you are familiar that tensors are mainly written in the form of matrices. So everything which apply to the matrices actually apply to tensors also. So you will learn about symmetric, skew-symmetric tensors. Then you will learn about tensor calculus and many other symbols, spaces and many other forms of tensors which you will be introduced to in later as a form of physical analysis of these tensors. In this video, I will be talking you about what is a vector. Then I will give you a brief introduction of tensor. Then we'll try to introduce you to stress tensor as a physical example so that you can grasp the idea behind tensor. And then give a formal mathematical definition for tensor. Let us understand vector. In our elementary classes, we have learned about vector as something which has a magnitude and a direction. But is everything which has a magnitude and direction a vector? Well, no. Consider reading a book. We read a book in a particular direction, that we read from top to bottom and from left to right. So it has a direction. We can't read it the other way around. And it definitely has a magnitude of what we read. We read maybe 2 letters or 2 paragraphs or 2 books. We have a magnitude of what we read. But the process of reading a book is not a vector. It definitely has a direction and a magnitude, but it's not a vector. Then why it is not a vector? Therefore, vector is not something which has a magnitude and direction. It also has to prove or also has to some laws have to be applied, and it also has to follow certain laws which can be mathematically explained. So a pure mathematical explanation for a vector is an element in a linear vector space. So to understand or to analyze a vector or to speak about the concept of vector, we need a space on the first and foremost. So the space we are used to is the 3-dimensional Cartesian space. So every space or every vector have to be analyzed in a space. In 3-dimensional Cartesian space, we have our basis vectors i, j, k, or any vector which is introduced in a space should have some basis vectors, and these vectors are to be introduced or to be analyzed in terms of these basis vectors. That is, vectors are given as a linear combination of basis vectors. Say some ai plus 2j plus 3k tells us about the vector, which says that the vector has some element which lies towards the I direction, some elements which lies towards the j direction, and some towards the k direction. And here we are talking about the position vector only. Suppose we are talking about a force vector. If we are talking about the force vector, then our linear vector space have to be that of force space. That is the force in the x direction, force in the y direction, and force in the z direction. Then our vector space is force space. If we are talking about momentum, then our linear vector space is that of momentum. And our basis vectors will be unit vector of momentum in the x direction, that in the y direction, and that in the z direction. So to talk about a vector, primarily we need to have a linear vector space, and a vector is defined in a vector space. And definitely it has a magnitude as well as direction, and it is represented, can be represented as a linear combination of the basis vectors of that particular vector space. And not everything which is defined in a space, a linear vector space, is a vector. It also have to obey the laws of vector algebra, that is vector addition, subtraction, the scalar product, and the vector product. So every vector or every element which obeys the laws of vector algebra has the term have to be defined as a vector. For example, say if I can I can write a vector r as a combination of r1 and r2, then only I can say it is a vector. So vector have to obey the laws of vector algebra, whether it is addition, subtraction. Mainly it have to obey the triangular law of vector addition as well as the parallelogram law of vector addition. So every element which obeys the laws of vector algebra are termed as vector. And another concept with the vector has to obey is the vectors are invariant under coordinate transformation. Let's see how it is. Now consider the vector r. Here we have a vector r which is defined in the space x and y, and let its coordinates be a and b. So I can write this vector r as ax cap plus by cap, and its coordinates here are a and b. Suppose I change my coordinate system. Let's say I change my coordinate system here to another coordinate system, x dash and y dash. And in this coordinate system, my position vector will have certain another corresponding vectors, such as say it is c as well as, therefore the vector r can be written as c x dash cap plus d y dash cap. So what actually changed is just the component of the vectors. Just the component of the vectors changed from a, b to c and d, and nothing about the vector has changed. Vector has always been the same. We can see that suppose we are dealing with a velocity vector. Suppose a ball is sliding and it has a velocity v, and let's say now I consider its velocity along an axis drawn in this direction and call it x and y and calculate the velocity. And later I decided to change my x and y and put it somewhere over here and again calculate velocity v. Does the velocity of the ball changes? No, only my frame of reference has changed. So with the frame of reference, what changes is just the coordinates of velocity or coordinates of that particular vector, and nothing about the physical properties of that vector changes. So the vector remains invariant under coordinate transformation, but its components may vary with that. Vector can be represented as a linear combination, as here I have written as ax cap plus by cap, and it can also be represented as a column matrix, and we will be sticking on to column metric representation in the coming slides also, because in tensors when we go for linear combination it's gonna be very cumbersome, so we are sticking on to a matrix representation. So vectors are represented as column matrix and its transpose are represented as row matrix. Vector is a first order tensor. So vector is nothing but a first order tensor. We will learn about order in our coming days. So for the time being, let's realize that to introduce a vector, a component of vector can be represented only with one element. Say A can be represented only with one base element x cap and B can be set completely set with one element y cap. We doesn't need more than one direction to completely establish one component. So here we need only one element to represent one component. So vector is a first order tensor. We will come to this later in detail. And examples of vector includes force and displacement. As we know, so force is represented in a linear vector space of force itself. Displacement is represented in the linear vector space of displacement. That is the real linear vector space we use, x, y, z space with our basis vector ijk. So displacement is represented in the normal R3 space as we see. Here you know R represent the real vector space of R3 actually represents the real vector space of dimension 3. This is the vector space we usually use. We go for R4 space in case of relativity. We'll come to that. And here the last I have to say that by understanding vector in such a mathematical rigorous manner, I should say angular momentum is not a vector but a pseudo vector. Let me control my point. So I have said that the vector should remain invariant under coordinate transformation. So let us consider a mass is being revolved around some point and its angular velocity, angular momentum will be taken in this direction and it varies according to the distance from the point. So its angular momentum actually about the distance from the point. So when the space or when my coordinate is passing extremely to the center of it, then the angular momentum will not vary. The angular momentum at every point directly depends on the distance from that point and it is always the same. So the angular momentum will not vary in case my coordinate passes through the center of that point. Suppose I have changed my coordinate from that point to another, then it will definitely change. Suppose I have shifted my coordinate point to this, then it will definitely change the angular momentum as angular momentum depends on the distance. So as the ball moves, the angular momentum decreases and then increases. But as we know that the physical quantity angular momentum remains the same, so considering this as the case, we can say that the angular momentum vector does not hold the property of invariance under coordinate transformation. So we choose, we have to say angular momentum is a pseudo vector. Hope I have given you a mathematical understanding of what a vector is. In the light of this, let us analyze what a tensor is. I have said vector is a first order tensor. So tensors are nothing but vectors which has an extra dimension. So I have to explain tensor as an algebraic object which has a multilinear relationship between the sets of algebraic objects related in a vector space. So tensor is also defined in a vector space. Instead of having a linear relationship, it has multilinear relationship with its basis vectors. That is, to analyze one component, we need to specify at least two directions. A vector had a magnitude and a direction, but a tensor has a magnitude and more than one direction. A vector obeys the laws of vector algebra, therefore the tensor obeys the laws of tensor algebra, and it is also invariant under coordinate transformation. We represented vector as a column matrix or a row matrix in case of transpose, and we represent a tensor as a two-dimensional matrix. And all these elements A11, A12 up to A33 represent the components of vectors. A11 represent the component of vector against the one direction, the first direction, say x direction, and it has two direction to be mentioned, so it is in x direction, and 33 is in z direction, while say 21 is in y/x direction. We will talk about this later in detail. So we represent a metric. We represent a tensor in the form of a matrix. Now, doesn't confuse here. Not every matrix is a tensor. A matrix is just a collection of elements in mathematics we use for analysis, but a tensor can be represented in the form of a matrix. So a matrix can be called a tensor only if it obeys all the laws of tensor. That is, when it is defined in a vector space, when it obeys the laws of tensor algebra, when it is invariant under coordinate transformation. So if a matrix obeys all these quantities, then we can call it as a tensor. So every matrix is not a tensor. A tensor can be represented mathematically as a matrix. A tensor has a very deep inner meaning than that of matrix. The first example I have to give you from physics is for a stress tensor. So stress is a tensor. We will come in detail to stress tensor. So stress tensor, here I have taken it as we can use tensors to map different vectors. Let us say I have a vector. If I have a vector A, I can multiply it with a scalar, and say if I multiply it with a scalar, then I will get another vector. But this is not essentially another vector. This is just a vector in the same direction which is being scaled by the scaling factor A. So by multiplication with a scalar, we are not going to obtain another vector, that is a vector which is in a different direction. So to obtain a vector in a different direction by multiplying something, we need to have a tensor. Say here we have force, and we can change it into a vector. Here we have area, and we can change it into a tensor, a vector force, which is another vector force, by multiplying this with a tensor sigma. And the stress tensor, which is normally denoted by sigma, and we denote tensors with a double bar or with bold letters. We will come to notations later. So what I have to say here is tensors can map different vectors. Not like scalars which can only scale vectors, tensors can actually map different vectors. And the examples of tensors from physics, which includes electromagnetic tensor, the stress tensor, the four tensors, the permittivity tensor, which we will come across later. So we have many tensors in physics, and these are all quantities which need to have two or more elements to represent that particular physical element. So two or more dimensions or two or more aspects has to be specified just to represent one physical quantity. So we will come across such physical quantities in physics a lot. So we use tensors to study them, and we use tensor analysis to study their properties. Now let me introduce you to the stress tensor so that you will get the complete idea of what I am talking about. So you are familiar with stress. We will suppose I have a cubical box, then I can give a stress, I can elongate them, and say I am defining it in my x, y, z direction. I can elongate them in the x direction, in the y direction, or in the z direction, or else I can just shear them. I can give a tangential stress. So there are two different types of stress, that is normal stress as well as tangential stress. So normal stress are given normal to the axis of the object, and tangential stress are given in an angle, with an angle with the direction. So I can give a tangential stress either in this way or in this way. So we can have normal stress as well as tangential stress. So to define stress, we cannot just define it using a vector, because it doesn't only have the x component, the y component, or the z component. Taking into account of the tangential stress has both the component in the x and the y direction, maybe x and z direction, z mixed components. So we need to have a tensor to encompass all these ideas, all these components of stress. So consider a box, and it is being represented in the x, y, z direction. And this box, say it has 6 phases, and I call 3 phases as positive phases. That is, the phases which are having its area vector, phases area vector towards the positive directions. That is, this space, I call it the positive x space. This is the positive y space, and here I have my positive z space. Okay, so I have 3 positive spaces and 3 negative phases. So I will consider these 3 phases, and everything happening here will be just opposite to what happening in the phase in its opposite direction. So the first stress which I can give here is this normal stress, which is completely normal to the direction. That is, I can give a stress in the z direction. I can either elongate or compress in the z direction normally to the surface. I can here elongate or compress normally to the x direction, and also elongate and compress normally to the y direction. So these are 3 normal stresses which I can give. Along with the normal stresses, I can also give tangential stress. That is, this tangential stress can be applied on the surface of z in the direction of x, or I can apply a force on the surface of z in the direction of y. So on the surface of z, I can actually give 3 different stresses. One is on the surface of z in the direction of z itself, and another is on the surface of z in the direction of x or negative x, on the surface of z in the direction of y or negative y. So here I have 3 different stresses which I can give on one particular phase one normal stress and one tangential stress. Here also, in case of this positive y phase, I can give a normal force, a normal stress on the phase of y in the direction of y. I can give a stress on the phase of y in the direction of this. This will just change the direction. The box will just shear in this direction when I give a force on this surface in x direction, and also I can give a force on this surface in the z direction. Same in the case of x also. Therefore, I have three types of normal stresses. Three types of normal stresses, that is the stress which is given. Three normal stresses, that is stress which is on the x surface in the x direction, stress on the y surface in the y direction, stress on the z surface in the z direction, and also different 6 tangential stresses, that is the stress on the x surface in the y direction, the surface which is on the x surface which is in the y direction. So it will shear, it will just shear this box towards forward. This will pull this box towards the forward direction. Okay, we have an force which is applied on the x which is in the y direction. On the contrary, see this component which is applied on the y surface, that is on the y surface towards the x direction. So it will shear this box towards the x direction. And similarly, we have the forces on the x surface towards y direction. On the y surface, we have force on x direction and y direction as well as y direction. And on the z surface, we have forces on the z, x, y and z direction. Since we have talked only about the positive phases, say we have a negative x phase here. So when it is applied on the surface, on this surface, then we have to take the negative of that. Suppose a force is on the negative x in the z direction, then it is minus xz. Just the negative of that. So the positive, the stress is taken positive while it is acting on the positive side in the positive direction. Suppose the force is acting on the y in the y direction, but it is towards the negative y direction, then the stress component will be negative yy. Similarly, on the contrary also, if it is acting on the positive side in the positive direction, then the stress is positive. Also, if it is acting on the negative side towards the negative direction also, the stress component is positive. Say if it is acting in the minus x phase towards the minus x direction, then the force component is sigma xx only. And the component, the stress component is taken as negative when it is acting on the positive side in the negative direction or acting on the negative side in the positive direction. This is just a matter of convention that what we take. It doesn't gonna change how we look into physically into the matter. Just this, I have to introduce you to these components. So here you can see we have 9 different components of stress. That is, in case suppose the stress was just a vector, if the stress was just a vector, we are going to have only 3 components, say sigma x, sigma y and sigma z, and it's done in a column vector. So here this is not the case because we have to account for the tangential stress also. That is, stress not just given in one direction. We have to account for on what surface the stress is given. So the first index here tells us about the direction of the area, and the second index here tells us about the direction of force. So we have two different indices which is represented here, where the first indices effectively tells us on which area the force is applied, whether it is on the plus x area or plus y direction of y area, on which area it is applied, and the second indices tells us in which direction it is applied. So let us say sigma zy tells us that the force is applied on the z face towards the y direction. So it is necessary for us to say the information becomes completely incomplete when we just say the force is applied in the z direction, because the force applied in the z direction can be applied from the x phase or a y phase or a z phase or a negative x or y or z phase. So it is very important to have a complete picture of the stress being introduced this particular box. We have to say this is applied on one particular phase in one particular direction. So the information about stress tensor is incomplete when we do not specify two different indices. So if the physical quantity itself tells us about how to specify, tells us how, that it need two different indices to specify these, two or more different indices to specify one particular component, then we have to use a tensor. In case of vector, we say the velocity, the information about velocity is incomplete unless we specify the direction in which the velocity acts. Just like that, the information about tensor is incomplete unless we specify at least two components, whether it is direction or whether it is any other physical quantity. When the physical quantity tells us that two different components have to be specified to understand one particular physical quantity, then that physical quantity must be a tensor. Now, let us define tensor in a mathematical way. In an m-dimensional space, a tensor of rank n is a mathematical object that has n indices and m to the power n components, and they obey transformation rules. With the help of stress tensor, I have to say a stress tensor is defined in a three-dimensional space and of rank n. Rank actually represent how many base vectors have to be there to specify one particular component. And here in case of stress tensor, the rank is 2, and because sigma rank actually represent the number of integers that we have, sigma ij. We have two integers, so we need to have at least two basis vector to represent one component of the tensor. So here the rank is 2. In that case, we have n to the power n components. Here it is 3 to the power 2 components, that is 9 components. This is true because we had a 3 by 3 matrix. So we had 9 components, and it does have to obey the transformation rules. We will come to transformation rules later. So for the meantime, let's understand tensor is a mathematical object or an element which is defined in an m-dimensional vector space, and it has a rank n, and it has a component, and it has m to the power n components, and it obeys all the rules of transformation. And the transformation rules in three-dimensional space are actually transformation rules we take from coordinate system to spherical coordinate system to polar coordinate system. Those transformation rules are what we are talking in the three-dimensional space. But in the case of the four-dimensional space, that is the Minkowski space, we have our number of dimension to be 4. Then the transformation we are here calling upon is the Lorentz transformation. And here we have 4 dimension because we take time as one extra dimension. Instead of 4 tensors, we also have 4 vectors there. 4 vectors for position, electromagnetism, etc. We have 4 vectors also there, and we have tensors. And in case of Minkowski space, the transformation we are talking about is Lorentz transformation, while in 3-dimension, the 3-dimensional space, the transformation we are talking about is the transformation and the orthogonal system transform. The rank of a tensor is the number of basis vectors which is needed to specify a vector completely. Here I am giving you an introduction, a glimpse about the electromagnetic tensor which we come across in general relativity. And here you can see that it is in a 4-dimensional space and it has only two matrices, two indices, that is its rank is 2 and dimension is 4. So it will have 4 to the power 2 components, that is 16 components. As you can see, it will have 16 components. Even though it was a 4-dimensional space, it had only rank 2 because each line we had a 0, so rank 4 was not needed. So here we have it's an example for Minkowski space. We will also be introduced to different tensors such as permittivity and permeability tensors. We know that permittivity and permeability is scalar in case of isotropic medium. We have values for these. In case of isotropic medium, we have definite values. These are scalars. But in case of an isotropic medium, these permittivity and permeability become tensors. That is, it will take different values when it is being measured in different directions. So the permittivity and permeability are also tensors in case of anisotropic medium. And here also we can see that this is defined in a 3-dimensional space and it has rank 2. So it will have 3 to the power 2 9 components. Similar here, it is defined by a 3 by 3 matrix. It is defined in a 3-dimensional space with rank 2, that is 2 indices are there, and therefore we have 9 components. Let me combine the ideas. There are different types of tensors. We know about scalars. Scalars are tensors of rank 0. We also know about vectors. Vectors are tensors of rank 1. Scalars need only one component to specify that body completely, that is magnitude only. Just a number can specify a scalar completely. All the information is embedded in just a number. In case of vector, we need magnitude and direction. In case of a 3-dimensional space, there will be 3 different directions. Therefore, at least 2 components, that is one magnitude and one direction, have to be there to specify a tensor. Therefore, tensor specify a vector. So vector is a tensor of rank 1. And in 3-dimensional space, it has 3 components. A dyad or a tensor of rank 2. We essentially call tensor of rank 2 as the tensor itself. So a dyad has a tensor of rank 2. It has a magnitude as well as 2 different directions. So in case of a 3-dimensional space, we will have 9 component and is represented by a square matrix. A triad, say for example what we take in case of relativity. The tensors are here we have our 3-dimensional is tensor of rank 3. So it has a magnitude as well as three different directions. That is, 3 basis vectors are needed to specify one component. So here we have, in 3-dimensional space, it will have 27 components. That is tensor of rank 3. When I say basis vectors, do not confuse that the basis vectors are just for the direction vectors. It is not just ijk. The basis vectors can be force vectors, that is, force in x direction, y direction, z direction. The basis vectors can be spin vectors. The basis vectors can be anything, a momentum, any physical quantity can be a basis vector. So in stress tensor we have just seen the basis vectors was just position vectors. But in case of other tensors you come across in different physical areas. So need not that everything has 4 different directions. It's just that we need 4 different elements to specify a physical quantity. That is, 4 different basis vectors to specify a physical quantity. Then that is a tensor. So let us summarize to you what we have learned in this lecture. So tensor are systems of components organized by one or more integers that can transform according to specific rules, that is, set of transformation rules. The number of integers is called the rank of tensors. The number of integers, that is ij, which we come across, it can be written as a subscript or a superscript. We will come to that later. So the number of integers in the component gives us the rank of the tensor. A tensor can be represented as an m by m matrix. In case we have m directions, then it can be represented as an m by m matrix. And the rank of the tensor is the number of basis vectors which we need to specify a component. And the tensor of rank n will have m to the power n components. The scalars and vectors which we know already are the tensors of rank 0 and rank 1 respectively. So in this lecture, I have tried to give a brief introduction, an idea about tensor. Our main chapter actually starts from our next lecture. So as a little homework, just try to familiarize with common tensors that we use in physics, find its dimension and rank. Also try to account for the same, why it has this number of dimension and why its rank is 2, why its rank is 3. Try to account for that. And also try to define the inertia tensor. You have learned about inertia tensor in the rigid body dynamics. Now let us try yourself to analyze each component of inertia tensor. Say if the inertia tensor Ix's, Ixy, Ixz, the inertia tensor also represented in the Cartesian system. So you can find that out and get the physical meaning, understanding of what the xy, the Ixy component represent to. What does the Izz component represent to? So just give try on inertia tensor and try to define all its components. Thanks for watching. Bye.